We are now going to discuss conic forms. Now, conic forms are new for most people. For most people, a conic form is something that's new. Now, there are four main conic shapes. Our conic shapes are hyperbolas, circles, ellipses, and hyperbolas or hyperbolas. So we got our parabolas, our circles, our ellipses, and our hyperbolas. Now, circles, these are really just special ellipses. To represent each conic form, we will use y minus k and x minus h. Similar to the point slope form where x1, y1 represented a point on the line, the point hk will either be a vertex or a center. Okay? And we're going to spell this Canadian way of center or center. Now, we have our vertical parabolas. This is something we're used to. And we have HK, the vertex. HK is the vertex of the parabola. A is the vertical stretch factor. And if A is greater than 0, then the parabola opens upward. If A is less than 0, then the parabola opens downwards. Now, one thing to note is that vertical parabolas are the only conic form that is a function. So this is the only conic form that is a function. Okay. Now we have horizontal parabolas. Now, horizontal parabolas, we have that HK is the vertex of the parabola. A is the horizontal stretch factor. And if A is greater than 0, then the parabola opens up right. And if A is less than 0, then the parabola opens up left. So here we have A greater than 0. Here we have A less than 0. If we look above, this was A greater than 0. And this is A less than A less than 0. Now, the only conic that is a function is the vertical parabola. All other conics are not functions as they do not pass the vertical line test. So what's our next conic form? Our next conic form are circles and ellipses. Well, many learn about circles well before ellipses. A circle is just a special form of an ellipse. The equation of an ellipse is as follows. The point in the middle here, the center, this is here, it's 1, 1. And in general, this is HK. The value HK is the center of the ellipse. A is the horizontal distance from the center to the edge of the ellipse. And B is the vertical distance from the center to the edge. If A equals B, then the ellipse is a circle. So here, circles are to ellipses as squares are to rectangles. So if we think about squares, it is a rectangle, but it's a rectangle where the width and height are the same size. Well, circles are ellipses, but the distance vertically to the edge of the ellipse and the distance horizontally to the edge of the ellipse are the same. That's what makes it a circle. Now, we can rotate ellipses. So if we have an ellipse and we rotate it using a rotation of our conic forms, that rotation means our distances are no longer going to be horizontal or vertical. They're going to be our distance to the most wide and our distance to the most high. And with a circle, the rotation doesn't change the most far and most high, because if those distances are the same, the entire shape will have the same distance. So we just got to be careful, but we're not going to be dealing with any rotated conic forms. We're just going to be dealing with unrotated conic forms. Our last conic form is the definition of the horizontal hyperbola. Now, here, our center point here, this is HK. That's our center point. And it's the center of the hyperbola. Now, AB is the reference box values. And the box has a center, HK. A is the horizontal distance from the center to the edge of the rectangle, or the edge of the reference box. And B is the vertical distance from the center to the edge of the reference box. The dashed lines are called the asymptotes of the hyperbola. Now, if we take this, we can go from the edge in. That is A. And now if I go up and down, that's going to be my height, B. And I use this to create a box. Then these dotted lines, what they are they are straight lines that go from the center to through the corner of the reference boxes. So these dotted lines go through the corners of the reference box, and then the hyperbolas go from touching here, touching the reference box there, and they curve and are asymptotic to these lines that go through the corner. So these dotted lines, they are our asymptotes of the hyperbolas. And when we're drawing a hyperbola, what we do is we mark the point HK. We then draw the box using A and B. So if I mark a point, then I'm going to draw a box using A and B. Then I'm going to create my asymptotes. And now, starting at the edge, if I'm a horizontal, I go up and approach, and I go up and approach. And then I go up and approach, and I go up and approach. Then what I can do is, after I'm done this, I can erase everything else if I want to, or I can simply leave it. This gives our equations for our horizontal hyperbola, or how we draw the horizontal hyperbola. Now the vertical hyperbolas are slightly different, and notice the change here. Here in our horizontal parabola, if in the circle we add here, what we're subtracting for the horizontal, and this is +1. Okay? So it's subtracting instead of adding. So in circles we add, horizontal hyperbolas we subtract, and our answer is 1. With our vertical, we're still subtracting, but our output is going to be -1. Okay? And now we have we have the same shape. We have our horizontal distance, our vertical distance. Whoop, I've drawn this box a little too big. Let me go out to the line, down, out to the line, meet up, cross, up, and across. This height is B, this height is A. A and B. So here, HK is the center of the hyperbola. AB is the reference box values. The box has a center, HK. A is the horizontal distance from the center to the edge of the reference box. B is the vertical distance from the center to the edge of the reference box. The dashed lines are called the asymptotes of the hyperbola. But we've gone through and we have 5 different conic forms. How do we determine which conic form it is? Well, it turns out that there's a general conic form. And there's actually a discriminant for determining which conic form we have. We can use the discriminant formula. If b squared minus 4ac is greater than 0, then the conic is a hyperbola. If b squared minus 4ac equals 0, then the conic is a parabola. And if b squared minus 4ac is greater than 0, then the conic form is an ellipse. Well, note that if a equals c, then the ellipse is a circle, not the eclipse, the ellipse. The term bxy is called the conic rotation. This will be ignored from now. From now on, we will only consider cases where b equals 0. In the future, you may look at conic rotations, and in those cases, what you'll typically do is you'll reorient your axes to make that conic rotation 0. But this is very much a thing within physics. Now, steps for computing a conic form. So given the general equation, we first group x terms and y terms. We group it together. We create this general form and we group them together. Then what we're going to do is we're going to complete the square for the x terms and complete the square for the y terms. Now, why are we doing this? Well, we're going to move all the constants to the other side of the equation sign. Everything gets moved to the other side of the equation sign. Then we're going to divide by the absolute value of the constant term everywhere. Then we're going to rearrange the scalars in front of x minus h squared and y minus k squared. Right? As we can see, in order to compute the conic form, we must complete the square. So before we practice solving our conic forms, let's review completing the square. So now what we're going to do is we're going to complete the square.